Class has seen some differences between ideal and non-ideal solutions. Non-ideal solutions are also known as real solutions. Okay. Of course, some important differences are: first one, the interactive force between the particles or molecules of solute and solvent in solution. See, in case of ideal solution, this interactive force between particles of solute and solvent in solution is almost same as that exists in case of pure solvent, pure components AA and BB. Whereas in the case of non-ideal solution, this interactive force is greater than or less than the force exists in pure constituents, that is between AA and BB. This is one important thing. Another one is, in case of ideal solution, delta V of solution is 0. That is, there is no change in volume of solution. That is, after mixing two liquids, there will be no change in volume. That means the resultant volume of the solution is just equal to the sum of the volumes of constituent liquids. That is, volume of solvent plus volume of solute, or volume of solution, liquid A plus volume of liquid B is equal to volume of the solution. Whereas in this case, this delta V is not equal to 0. That means in one case delta V will be positive, in another case delta V is negative. That is, in case of non-ideal solution, delta V change in volume will be either positive or negative, but not 0. Another difference you have seen, that is enthalpy of solution, delta H of solution. In case of ideal solution, during the formation of solution, enthalpy change is 0. That is, formation of solution is thermoneutral, neither positive nor negative. That means formation of ideal solution of binary liquids is neither exothermic nor endothermic. It is not so in the case of non-ideal solutions. In the case of non-ideal solution, delta H is not equal to 0. That means delta H may be positive or delta H may be negative. That is, formation of solution may be endothermic or exothermic. Okay. Another point is, in the case of ideal solution, that is in the plot of vapor pressure against mole fraction is a linear. The plot of vapor pressure against mole fraction in the case of ideal solution is a linear. That shows the vapor pressure of mixture, that is combined vapor pressure of solution, lies in between the vapor pressures of pure components. Vapor pressure of solution lies in between the vapor pressure of pure components at all composition. Here it is not so. In the case of non-ideal solution, the combined vapor pressure of the solution or mixture will be either higher or lower than the vapor pressures of pure components. So these points are the important differences, main differences. Of course, there are some more differences between ideal and non-ideal solution. Now we shall see the reason for these differences. Delta V for ideal solution is 0. That is, there is no change in volume, because in the case of ideal solution, the distance between the solute particle and solvent particle, or distance between the particles of two constituent liquids in the solution, is same as that exists in the case of pure constituents. So there will be no change in volume. Volume remains same. That's why delta V is 0. Here delta V will be positive or negative, but not same. But not 0, because in this case the distance between A and B, the intermolecular distance or intermolecular force of attraction, of course they are related with each other. The intermolecular force of attraction or distance between the particles of constituent liquids in the solution is not exactly same as that exists in the case of pure components. So after mixing the components A and B, that is constituent liquids A and B, while forming solution, the distance between the particles may be increased or decreased. If increased, volume also increases. If decreased, volume also decreases. So both can happen. In some cases, increase in volume takes place. In some cases, decrease in volume takes place. That's why delta V is not equal to 0. Okay. Next one, delta H is 0. Once again, the same reason. During the formation of solution, while condensing the particles of solute, heat is neither absorbed nor liberated in case of ideal solution. Hence, enthalpy of solution is 0, or formation of solution is thermoneutral. Whereas in the case of non-ideal solution, during condensation of particles, heat may be absorbed. Heat may be absorbed. That is, in the case of increasing the volume, increasing the distance between the constituent particles. During condensation of solute particles, heat is absorbed. That process is endothermic. Therefore, delta H is positive. In some cases, that is, while decreasing the distance, heat is liberated. During decrease in volume, heat is liberated. They are exothermic in nature. That process is exothermic in nature. And see, these points of non-ideal solutions indicate non-ideal solutions are of two types. There are two types of non-ideal solutions. Some non-ideal solutions show positive deviation from the Raoult's law. Some solutions show negative deviation from the Raoult's law. So there are two types of non-ideal solutions. They are said to be non-ideal solutions showing positive deviation from Raoult's law and non-ideal solutions showing negative deviation from Raoult's law. Okay. See, I will give few examples. Of course, we have seen the differences also between non-ideal solution showing negative deviation, non-ideal solution showing positive deviation. See, in non-ideal solution showing positive deviation, one is A, interaction between A and B, that is particles of solute and solvent in solution is greater than, distance less than interaction between AA and BB. So when interaction is less, distance is more. Okay. In such case, delta H is positive and delta V is positive. Okay. 3 points here. In case of non-ideal solution showing negative deviation, the interactive force between the constituent particles is greater than that exists in pure solvent, that is AA as well as BB. And delta H is negative. It followed by absorption of, liberation of heat. This process is exothermic. This process endothermic. Here volume increase takes place. Here volume decrease takes place because attractive force is more. As the result, the particles come closer. Consequently, size decreases. Therefore, final volume is less than the sum of the initial volumes of constituent liquids. Next one is, see here the plot of P versus mole fraction of constituents show a maximum. It is actually curve showing a maximum like this. Here that plot is also a curve showing a minimum. That means the combined vapor pressure of the mixture will be less than the vapor pressures of pure components, tall compositions. Here the combined vapor pressure is higher or greater than the vapor pressures of pure components at all composition. So these are some differences between non-ideal solutions showing positive deviation and non-ideal solution showing negative deviation from Raoult's law. See, I will give some examples for positive deviation. Non-ideal solution showing positive deviation. See, mixture of acetone and ethyl alcohol. Ethyl alcohol. See here, acetone when mixed with ethyl alcohol. In ethyl alcohol, there are actually in ethyl alcohol system, ethyl alcohol molecules are joined through hydrogen bonds. Ethyl alcohol molecules are joined through hydrogen bonds. See, when you add acetone to ethyl alcohol, some hydrogen bonds are broken and the space created there acetone molecule occupy. As the result, distance increases and attractive force decreases. So this system shows positive deviation from Raoult's law. See, in the case of binary liquid mixture, if solute breaks the hydrogen bonds of solvent, that system or solution show positive deviation because of increase of volume of the system. Sometimes the solute which can decreases the dipole-dipole interaction in the system, there also one can observe positive deviation from Raoult's law. That is, for that the example is acetone in carbon disulfide. See here dipole-dipole interaction is reduced, whereas here hydrogen bonds are broken, which leads to deviate from leads to positive deviation from Raoult's law. Next example for negative deviation. See, HCl and H2O. HCl and H2O shows negative deviation. When you mix concentrated hydrochloric acid with water, volume of resultant system decreases. Here, even when you mix ethyl alcohol with water, volume increases. Increase ಆಗುತ್ತೋ ಇಲ್ವೋ ವಾಲ್ಯೂಮ್ ಅನ್ನೋದನ್ನು ಈ ಆಲ್ಕೋಹಾಲ್ ಕನ್ಸ್ಯೂಮ್ ಮಾಡ್ತಾರಲ್ಲ ಅವ್ರನ್ನ ಕೇಳಿ, ಅವರು ವಾಟರ್ ಜೊತೆ ಮಿಕ್ಸ್ ಮಾಡ್ಕೋತಿರ್ತಾರೆ, ವಾಲ್ಯೂಮ್ ಜಾಸ್ತಿ ಆಗುತ್ತೋ ಇಲ್ವೋ ಅಂತ ಕೇಳಬಹುದು ಸಿಕ್ಕಿದ್ರೆ. ಓಕೆ, ನೀವು ಟೆಸ್ಟ್ ಮಾಡೋಕ್ಕೆ ಹೋಗಬೇಡಿ. HCl and water system show negative deviation. Similarly, sulfuric acid water, nitric acid water show, of course, they are non-ideal solution showing negative deviation. In case of non-ideal solution showing negative deviation, hydrogen bonds are formed. Illi hydrogen bonds are broken. In this case, hydrogen bonds broken. In this case, hydrogen bonds form. Just I will give an example. Acetone and chloroform. Mixture of acetone and chloroform, that is solution of acetone and chloroform, is a non-ideal solution showing negative deviation. Here, hydrogen bonds formed. When hydrogen bonds formed, molecules or particles come closer, consequently size decreases, volume decreases. Okay? During that process, heat is liberated, delta H is negative. Okay? Where the distance between A and B is interaction between A and B, or interactive attractive force between A and B particles is greater than that exists in pure components. See here, acetone, you can write acetone CH3CO CH3. Okay, this molecule can polarize. Here, polarity takes place to form or to give delta minus, delta plus. Okay, when acetone molecule polarized, charges accumulate on carbon and oxygen like this. Now consider your chloroform. Chloroform is, okay, these are electronegative elements, attract the electrons towards them. As a result, hydrogen gets positive charge. Now a sort of bond develops between hydrogen of chloroform and oxygen of acetone. This bond is known as hydrogen bond. Because of formation of hydrogen bond, attractive force increases and shows negative deviation. So this is about the non-ideal solutions showing positive deviation and negative deviation from Raoult's law. Next bit is azeotropes. Before that, I would like to give the plots of pressure, vapor pressure against mole fraction of constituents of ideal solutions and two types of non-ideal solutions. You know, for ideal solution, the plot of mole fraction against total pressure or vapor pressure, consider chi of A, here it is 0, and chi of B, here it is 1, chi of A 1, chi of B 0. Just see, when you move from left to right side, mole fraction of A, constituent A, increases. At this point, only pure A present but not B. Here, constituent mole fraction of constituent B increases from right to left. If solution is ideal, plot will be like this. Okay, this is for solution A. For not solution, for solvent A or component A, this is for component B, and okay, this plot, this is for solution, we can write. Okay, this is for PA, PB, this is solution pressure, total pressure, and of course this pressure is PB, partial pressure or vapor pressure of pure component B. This is vapor pressure of pure component A. This is the shape of plot of vapor pressure against mole fraction of an ideal solution. Okay. For non-ideal solution, let us see the plots for non-ideal solution showing positive deviation and negative deviation. Mole fraction against total pressure. Let us see dotted line plots are the plots for ideal solution. These are the plots of ideal solution. For non-ideal solution showing positive deviation, non-ideal solution showing positive deviation shows higher vapor pressure of mixture than constituent liquids at any composition. That means, in the case of non-ideal solution showing positive deviation, the plot of pressure, vapor total pressure against mole fraction shows a maximum. It is something like this. Plot will be like this. And of course, for the constituent liquids are like this. Single stroke line or for the non-ideal solution, dotted lines for ideal solution. Here this plot, it shows the combined vapor pressure of the mixture is higher than the vapor pressures of pure components, and show a maximum at any composition. Okay. In case of non-ideal solution showing, this is in case of positive deviation, non-ideal solution showing positive deviation. Non-ideal solution showing negative deviation, the plot will be like this. Chi pressure, of course, for ideal solution, these are the plots. Okay. Here vapor pressure of one of the pure component, here vapor pressure of another pure component. So in case of non-ideal solution showing negative deviation, the vapor pressure, combined vapor pressure of the mixture is less than, it is actually less than the vapor pressures of pure components at any composition. And plot is actually a curve showing a minimum. The plot will be like this, okay, showing a minimum. And for corresponding liquids, also plot like this. Okay, these are the plots of ideal solution, non-ideal solution showing positive deviation. Positive deviation means the curve must show maximum. Negative deviation must show a minimum. Okay. Another thing is, the liquids which have low boiling point show high vapor pressure. Boiling point low, corresponding liquid show high vapor pressure. Lower the boiling point, higher the vapor pressure. Higher the boiling point, lower the vapor pressure. That's why volatile liquids often show high vapor pressures, because they can easily vaporize even at ordinary temperature. The plot of boiling point against mole fraction of these three types of solution will be same but inward. See, vapor pressure is inversely proportional to boiling point. Lower the boiling point of the liquid, higher will be the vapor pressure. Higher the boiling point, lower will be the vapor pressure. Okay. So, these plots are inverted. When you plot taking boiling point as a function of mole fraction. That's about the plots of ideal solution, non-ideal solution showing positive deviation as well as negative deviations. Next, we shall see another important thing here, azeotropic mixtures or azeotropes. See, one of the difference between ideal and non-ideal solutions shows or says ideal solutions can be subjected to fractional distillation, where we can separate the constituents in their pure form. That means the constituents of ideal solutions can be separated by means of fractional distillation. Fractional distillation means distillation carried out at different temperatures. So, in case of ideal solutions, the constituent liquids can be separated by fractional distillation method. Whereas, in case of non-ideal solutions, the constituent liquids cannot be separated by fractional distillation into their pure components. It is not possible to separate the constituents liquids of non-ideal solution into their pure form by fractional distillation method. Okay. See, the binary liquid mixtures of non-ideal, particularly non-ideal binary liquid mixtures which have same composition in vapor phase as well as in liquid phase at the boiling point are known as azeotropes. Azeotropes or azeotropic mixtures are those binary liquid mixtures of non-ideal type which have same composition in their vapor state or liquid state at the boiling temperature. or else you can say non-ideals, isotropic mixtures are the solutions or binary solutions which cannot be separated by fractional distillation method, or azeotropic mixtures are those binary liquid mixtures which boil at a temperature, without change in composition, Example, you can give any non-ideal solution as example. Say ethyl alcohol, water. Mixture of ethyl alcohol and water on fractional distillation, you will get a product of 95.5% alcohol. 95.5% alcohol, that is rectified spirit, from which the remaining part of water cannot be separated by fractional distillation. Okay. So, mixture of ethyl alcohol and water, methyl alcohol and water, acetone, chloroform, acetone, carbon disulfide, etc., etc., etc. See, the negatively non-ideal solution, that is non-ideal solution showing negative deviation from Raoult's law, are considered as minimum vapor pressure azeotropes, whereas positive deviation non-ideal solutions are known as maximum vapor pressure azeotropes. Whereas in terms of boiling point, positive deviation mixtures are said to be maximum boiling point azeotropes, and negative mixtures are said to be maximum boiling point azeotropes. So, this is about azeotropic mixtures as well as the solutions of liquid in liquid. Now, we shall pass on to another part of the solution, another type of solutions, that is solutions of solid in liquid. Solutions of solid in liquid. So far, I have studied solutions of gas in liquid, solutions of liquid in liquid. Now we shall see solutions of solid in liquid. Earlier, I have seen the factors which influence on the solubility of solid in liquid. Generally, nature of solute, nature of solvent play important role on the solubility. Another point, temperature also plays a significant role on the solubility of solid in liquid. Pressure normally has no influence on the solubility of solid in liquid, because solid and liquid have high incompressibility. Therefore, pressure has no influence on solubility of solid in liquid. Dilute solution, particularly dilute solutions of solid in liquid. What do you mean by dilute solution? A dilute solution is one in which amount of solute present is very, very small compared to amount of solvent, or solution in which a small amount of solute is dissolved in a quite large amount of solvent. The resultant solution is said to be dilute solution. Normally, concentration is very, very low. The dilute solutions of solid in liquid often exhibit type of properties known as colligative properties. Colligative properties. So, colligative properties are the properties of dilute solutions of solid in liquid. Then what are these colligative properties? Colligative properties are the properties of dilute solutions of non-volatile and non-electrolyte solute. It is also important. They are the properties of dilute solutions of non-volatile and non-electrolyte solutes, which entirely depends upon number of particles of solute present in the solution rather than their nature. The properties which mainly depend only on number of particles rather than nature are known as colligative properties. I repeat, colligative properties are the properties of dilute solutions, particularly solid in liquid solutions, which entirely depend on number of particles of solute present in the system or solution. Number of particles of solute present, but not the nature of particles, nature of solute particles. That is colligative properties. The general or the important colligative properties are relative lowering of vapor pressure, relative lowering of vapor pressure. Second one, osmotic pressure, relative lowering of vapor pressure. Osmotic pressure, relative lowering of vapor pressure of solvent. Osmotic pressure of solution. Elevation in boiling point of solvent. Elevation in boiling point of solvent. And depression of freezing point of solvent. These are the four colligative properties exhibited by dilute solutions. Now we shall study these properties one by one in the next class.